Alright, here's the answer key for the worksheet for carboxylic acids. Here we're looking at the acidity of course, these carboxylic acid functional groups here. And really the differences stem from the substituents on the aromatic ring. We have a ketone, we have a chloride, and we have an ether. This is electron donating, while the other two are electron withdrawing. So we know that acidity increases with the availability or the presence of electron withdrawing groups. And in this case, the ketone is more electron withdrawing or has a greater electron withdrawing effect than the chlorine does. And so the ketone is the most acidic. The electron donating group, which would actually decrease the acidity of the starting carboxylic acid, gets ranking of number 1. Here's some more rankings of acidity, and here we have just a standard carboxylic acid, no aromatic group. We have different length chains, and we have different electron withdrawing groups present, or 0 electron withdrawing groups present. So in this case, we want to look at the type and the number and the location of the electron withdrawing groups. Chlorines are electronegative, but fluorines are more electronegative, and so this molecule, trifluoroacetic acid, is the most acidic. These have the greatest electron withdrawing ability, and so they'll stabilize the O- to the greatest degree. And so the trichloroacetic acid would be the next most acidic. Then we have this chlorine that's a few carbons away from the carboxylic acid versus acetic acid, which has no chlorines. And so this one would be the next most acidic, but it only wins slightly over the acetic acid. So I would say these two compounds are pretty close in acidity. And we'll say that this one is slightly more acidic because it has this electron withdrawing group with an inductive effect. There's no resonance here, it's just proximity to the OH that's in question here. This inductive electron withdrawing group is farther away, and there's only one of them, but it's still present, and so that's why we make acetic acid have the lowest acidity of these 4 molecules. For the question 3, which of these reactions would occur at the faster rate? Well, we can observe that they are essentially the same reaction. We would end up with this product, not counting any byproducts. So we're making the same product. We're undergoing essentially the same reaction, except that we have an anhydride here and an acid chloride. All we need to answer this question is to remember the order of reactivity. Acid chloride greater than anhydride, greater than ester, greater than amide. So whichever of these is present, or I'm sorry, the highest one that's present, in this case is the acid chloride, so the correct answer would be to circle this reaction scheme. Here we're asked to predict the product of these reactions. So we have an amine, we have an anhydride, and we know that the leaving group is essentially this piece of the anhydride. And so the product would look like this. We're going to take the NH, substitute one of the H's for the remaining half of that anhydride. And the byproduct, which we don't necessarily have to draw, is that carboxylic acid, propionic acid. Here we have an amide, which we just made here. This is also an amide. And we're going to undergo acidic hydrolysis. So we're going to add water to the amide, use acid as a catalyst. We're going to end up with substituting the NH2 into an OH. And we end up with NH3 as a byproduct, but really it's NH4 because we're under acidic conditions. So as soon as the NH3 is formed, it is a good base. It picks up this extra hydrogen here. This third one is simply an acid-base reaction. We have an acidic hydrogen right here, and we have a strong base, NaOH, and so it's really as simple as that. We make the carboxylate, the O-, and we have associated with that sodium cation. And then the HOH is produced, and of course that's just H2O, water. Here we have an ester reacting with some strong base, and if you remember from the text or the video, this is called saponification. so really what we're going to end up with is the carboxylic acid and the alcohol. Here we have an acid chloride plus an alcohol. We just saw that reaction in the previous question. It's basically substituting the Cl for the O-ethyl. And of course the byproduct here is HCl. And in practice we'd have some base here that would then combine with the HCl so that we don't have this strong acid floating around in our organic system. Here we have an anhydride and an alcohol. Again, same reaction as previously. We'll get the same product except we have a different shape, or a different type of anhydride in this case, and then the byproduct then is the carboxylic acid, in this case acetic acid. Here's an anhydride plus an amine. Same concept, we're going to substitute this piece, the leaving group, with the nitrogen plus its R group. And of course the byproduct then is, again, carboxylic acid. And lastly we have what's called a Fischer esterification. We're going to change the carboxylic acid, the OH, into an OR group. We're going to make an ester. And of course the byproduct is water. We lose this OH and this H to make water. And so that's called Fischer esterification. We make this ester here. The final question on this worksheet asks for the mechanism of this problem. The product is given as this. So we're asked for the mechanism of this acid chloride reacting with the alcohol. So the first thing we need to do is draw the lone pairs in, because those are going to play a large role in the nucleophilicity of this alcohol. And we know that we can attack carbonyls because they have this permanent dipole moment, and we can push electrons onto the O, producing this tetrahedral intermediate. That gives us this protonated compound. And we can use this pyridine to remove the extra hydrogen, reducing one of these formal charges to neutral. And then we can reduce the other formal charge by dropping the lone pair on oxygen back down to form the CO double bond, losing this good leaving group, the Cl- compound, or ion. And in fact, that brings us to the product. So we reform the double bond, we lose chloride, here's our chloride. We now have this ester, and we formed this pyridinium salt in this step right here. So that's the mechanism of alcohol reacting with acid chloride to produce an ester.